everyone, this is Mike coming back at you with another video on discrete mathematics. In the previous video, we introduced ourselves into Chapter 3. We talked about the steps necessary in the proof technique of direct proof. And then we went through some basic definitions about numbers being even and odd, just to give ourselves some definitions that we'll use when in our next video we do several sample proofs of some very basic math facts. But in this video, I just want to take a quick couple minutes or so, just go through a couple more mathematical definitions and a couple more basic facts, which we will use again in our next video to perform some sample proofs on these related properties that we really use implicitly and we just take for granted, but we still have to prove these things to formally know that these things are true. So first thing I want to just talk about is the definition of a rational number or a fraction. A rational number is a number that can be expressed as a quotient of two whole numbers or integers, with the denominator not being 0. The formal way that we say this and the formal way we represent the set of all rational numbers, which is that fancy Q, it's the set of all things of the form P over Q, where P and Q are integers or whole numbers and Q is not equal to 0. And with this definition, we can prove some very basic facts about taking sums of rationals or differences of rationals or anything like that. But we will do some of those in our next video. And now I want to go into some number theory definitions and some number theory theorems. First one, let A and B be integers. We say that A divides B if B is equal to A times K, where K is some whole number. So A divides B. The other way we would say this, and you probably have said this more often this way, is B is divisible by A. So B is divisible by A, or A divides B, both saying the same thing. And what they're saying is that B is equal to A times K for some integer K. If A divides B, we have a special symbolization for that. We write A and then a big vertical bar and then B. There's a very basic yet very important theorem in number theory that I just wanted to show you. It's called the quotient remainder theorem. So let A be an integer and let B be a positive integer. And we assume that A is greater than B. Then there exist integers Q and R such that A can be written as Q times B plus R. And this R here has the property that it's greater than or equal to 0, and it's strictly less than B. Now this quotient remainder theorem right here, this isn't a massive thing that pops up in this course, so this is just something I want to show you. If you go on to take elementary number theory, then you'll see that coming up more in that course. And then a last couple definitions that I just want to show you. If you have any real number x, so it could be a whole number, it could be a rational, it could be an irrational, the floor of x, and it is denoted with an x, what looks to be in the middle of a regular capital L and a backwards capital L. The floor of x is the unique integer n such that n is less than or equal to x, which is less than n plus 1. Another way to say this is that the floor of x is the unique whole number n that is less than or equal to x. So case in point, if I had, say, the number 3.5, and I plug this into my floor of x function, what is the greatest whole number that is less than or equal to 3.5, that number is 3. It's the greatest whole number that is less than or equal to x. If I plugged in, say, 10, then the greatest whole number that's less than or equal to 10 is 10. So that's just a couple basic samples of what the floor function does. Similarly, the ceiling function, or the ceiling of x, and it is denoted with x and what appears to be in the middle of an upside down capital L, and then a backwards and upside down capital L. The ceiling of x is the greatest whole number, n, that is greater than or equal to x. So case in point, again, say I had x was 3.5. What is the greatest single whole number that is greater than, or my apologies, let me back that up. The ceiling of x is the least unique whole number n that is greater than or equal to x. So once more, let me clarify. The ceiling of x is the least unique integer n that is greater than or equal to x. So now, back to my sample here. If I have x as 3.5, what is the least integer that is greater than or equal to 3.5? Well, that's 4. We have obviously many more that are greater than 3.5, but the smallest one, the least one, is 4. If I plugged in minus 7.5, then the smallest integer that is greater than or equal to minus 7.5 is minus 7. So these are just a couple more samples here, a couple more cases where we use the ceiling function. So these are all the basic definitions and just terms I wanted you to see. In our next video, as I said, we'll be doing several sample proofs. We'll see how we write these things up, we'll see how we structure them, and we'll see what a properly written proof should look like. If you have any questions or comments, be sure to drop them in the comments section below. Otherwise, until the next video, take it easy, guys.